Yes, good morning. Today we're going to talk about Chapter 8, or begin talking about Chapter 8, entitled Hypothesis Testing. Well, as we know, an hypothesis is not an educated guess. An hypothesis is nothing more than a claim. A claim that something is true, whether it be a population proportion, a population mean, a population standard deviation, whatever. In the realm of statistics, we say that an hypothesis is a claim. And today we're going to talk about section 8.3. I'm going to kind of marry 8.2 and 8.3 together in our text. And in 8.3 we're going to talk about testing a claim about a population proportion. As we know, populations can sometimes be huge, and if you're interested in a population proportion of some characteristic of interest, well, really what we're going to do is make claims about lowercase p. All right, little p is our designation for population proportion, again with some desired characteristic. And as we know, populations tend to run huge, so little p in fact is unknown and indeed unknowable. What we will do is again take a sample, and from a sample we can compute a sample proportion with that same characteristic of interest, and the notation for sample proportion is p hat. Typically this symbol is called p hat in the realm of statistics. P with a little caret on top. P hat is sample proportion, okay? Alright, so we are going to use our sample proportion to test a claim about population proportion. And we're going to do that with a scheme called hypothesis testing. Let's suppose a claim, an hypothesis, is made about population proportion of left-handed people. We've talked about that in a similar realm in this course before. Alright, so a claim is made that the population proportion of left-handers in the world today is 10% or 0.1. Suppose further, from a sample, we get some new information. Let's say we take a sample of 110 human beings, and from that sample we arrive at 13 of those 110 people are lefties. So X is going to be our raw score, or our raw count of left-handed people in this sample. Hence p hat, our sample proportion, is nothing more than the number of lefties, 13, divided by 110. And if we grind that out in a decimal, we get 0.118. Alright, so we get this sample proportion, and the crux of the matter here is, does this value from the sample enable me to claim this is false? Right? So the real idea here is, well, let me write this down. Based on the sample proportion of 0.118 of left-handed people, can we reject the claim that the population proportion of left-handed people is 0.1? Can we reject this claim based on this sample data? Alright, and of course you're wondering, well, is this data strong enough to reject the assumed claim of 10% of 0.10? At what value of p hat will we reject the assumption that P is indeed 0.1. Is 0.11 strong enough? 0.12, 0.13, 0.15? At what value of P hat will we reject the original claim? In other words, when does the sample data become statistically significant? And again, we hear that word all the time. When is your sample data statistically significant with regard to rejecting the original claim? Alright, so this is really the crux of the matter here, and this is what we're going to be investigating the rest of the day. Let's talk about some notation first with regard to hypothesis testing. H sub 0 by convention is referred to as the null hypothesis in hypothesis testing, or some books call it the null claim, because a claim is an hypothesis, right? H sub 1, again by convention, is referred to as the alternative hypothesis. All right? And again, by convention, when we're testing claims one against the other, the null claim or the null hypothesis is always an equality statement. All right? In the previous example, it would have been that P equals 0.1 for the 10% of left-handers. H1, the alternative claim or alternative hypothesis, is always, well, it's always an inequality. It's either a less than statement, a greater than statement, or an inequality statement. Right? In the case of H1 being a less than statement, we will then call it a left-tailed hypothesis test. In case H1 is a greater than statement, we would then call it a right-tailed hypothesis test. And if H1 is a not equal to statement, we call that a two-tailed test. So please note that the sign in H1, let me write this down, the sign in H sub 1, or the alternative claim, determines the type of hypothesis test. Either right-tailed, left-tailed, or two-tailed. Okay? P, as we know, in section 8.3 will represent our population proportion with some characteristic of interest. P hat, as we know, will be our sample proportion with that same desired characteristic of interest. N is going to be our sample size, and alpha is going to be our significance level. Right, this will, informally be the bar that we have to overcome to reject the null hypothesis or the null claim. Typical levels for significance level are 0.1, 0.05, or 0.01, kind of a low, medium, high scenario for setting the bar or the burden of proof which the H1 claim must overcome. Alright, we are going to use the p-value approach. In all hypothesis tests in this course. Alright? There's a classical approach, some books call it traditional approach, some books call it a critical value approach. But we're going to, in favor of integrating technology here, use our p-value approach, and the calculator will compute this for us. p-value. And in section 8.3, which we are in today, we're going to use the one proportion, because we are interested in claims about proportions, one proportion z-test command, of course, found under your stat menu. Alright, we use the z-test command on our calculator, and because the calculator can upstream or internally computes p-value using really the z-scores of sample data. Alright. So hence, since the calculator uses z-scores, we want the one prop z-test command. If you're interested, the formula for the z-score of a sample proportion, it should look somewhat familiar to you. Z-score of your sample proportion is p hat minus p divided by the square root of p times q over n. Again, the calculator does all this internally. You plug in the sample data and the calculator essentially will spit out a p-value. Alright, let's talk a little bit about p-value. P-value, well, informally it's the right tail area determined by a sample proportion, or I should say the z-score of a sample proportion. If your sample proportion is in an extreme high range, this shaded area is going to be my p-value. And if your p-value is small, that tends to infer that your sample proportion, or the z-score of your sample proportion, is in extreme ranges, right? So if your p-value is small, that means your sample data is statistically significant. And indeed suggests that we reject H0, reject the null claim. If your p-value is large, well, your p-value is nothing more than the right tail area determined by the z-score of your sample data. Right, let's say I've got a z-score that gives me a high area, or larger area, right of my z-score under the normal distribution. If your p-value is large, that tends to say that your sample data is not extreme, or your sample proportion is not significant. And in that case, our data is weak. And here, in this case, we suggest that we fail to reject H0. Alright, let me get a fresh screen and kind of summarize those two statements. Small p-values. And again, your p-value is determined by your sample data. The calculator computes it for us. Small p-values suggest H0 is false. And in that case, our conclusion would be to reject the null claim in an hypothesis test. larger p-values, conversely suggests that h0 is true. And in that scenario, I would fail to reject h0. Alright, so your hypothesis test type questions will always be answered with one of these two statements. Either we reject h0 or we fail to reject h0. Alright, let's run through a quick example here of how we do this, and I've got it broken down to a three-step process. Let's talk about step 1. Well, let me write down the scenario first. Let me formally write it down here. Example. A sample of 110 adults yields 13 left-handers. I'll abbreviate that as lefties. I'll say test the claim. And bells should go off when you hear this phrase, test the claim. Test the claim that the population proportion of left-handed people is greater than 0.1. And I'll say use a 0.05 significance level. Okay? Alright, so we want to test the claim. Well, the claim is an hypothesis. What claim? That the population proportion of lefties is greater than 0.1. Alright, so let me write that down. Little p is greater than 0.1. Alright, so that's going to be our claim that we're going to put under the knife here. And remember, H1 is always an inequality statement. Alright, so either H1 or H0 typically is given to you in the context of the problem, and you kind of have to unravel it from the words. Alright, if H1 is the claim that P is greater than 0.1, then by inference, the null claim, H0, is that little p is 0.1. Alright, so this is step 1 in any hypothesis test. That's to state the hypotheses. And they always should be in this format. H0p equals something, or H1p is either greater than, less than, or not equal to something. This is going to be a right-tailed test. We're not going to reject H0 unless we're very sure that little p is greater than 0.1, and greater than infers a right-tailed test. Again, the sign in H1 always determines the type of test. Alright? Step 2. Compute the p-value of your sample data. Now again, the p-value, informally, it's the extreme right tail determined by the z-score of your sample data. Here it's a sample proportion. Now the calculator computes that for us, so let me write down this new command. We're going to use the one proportion or one prop z-test. Prop because we're talking about a population proportion, and z-test because the calculator will use a z-score to compute our p-value. So one prop z-test in section 8.3. Alright, let's introduce that command. As you might guess, it falls under the test submenu. So on your calculator, press stat, then test. We've been there before, and it's a new command under that test submenu called one prop z-test. So highlight that command and hit enter, and the calculator prompts us for some things to enter. First thing they ask us for is P sub 0. Well, this is the Texas Instruments lingo for the null hypothesis. Let me write that down. This is TI symbol for, well, in this example, it's going to be the null hypothesis that P equals 0.1. All right. So what I'm going to enter in here is P sub 0 colon 0.1 or 0.10. Okay. Again, that's the TI lingo for the null hypothesis. It's kind of shorthand for that null hypothesis. Next thing the command prompts us for is a raw count for the left-handers in our sample data. Well, of course, that's 13. And let me label that. This is a raw count of lefties in our sample. Okay? Alright, once we enter those two items in, the calculator prompts us for a sample size, and of course that's 110. Little n is always our sample size, right? Now the next thing the calculator prompts us for is the type of test. And again, TI uses their own shorthand for this. And we've got three options. Either for a left-tailed, right-tailed, or two-tailed test. Alright, this is a right-tailed test. We are interested in if our sample data reveals a sample proportion greater than our null claim. So I highlight greater than P sub 0, select it and highlight. Again, this part of the command selects the type of hypothesis test, and here it's going to be a right-tailed test. Alright, once I enter in all that data, of course I'll highlight and select calculate and get the following result screen. Alright, the calculator tells us prop greater than 0.1. Well, this is really the TI lingo. I'll say TI lingo for the alternative hypothesis. Remember, the alternative hypothesis was P greater than 0.1. The calculator also returns a z-score. Now that is the z-score of the sample proportion according to the formula I gave to you earlier. We are not going to use that directly here. The next line is the one that counts. It's kind of a strange looking P. This is the money ball right here. This is my p-value. This is what I'm really interested in, p-value. And for these hypothesis tests, the p-value will tell it all. The calculator also returns a p-hat value. That's a sample proportion, and also returns a sample size that you already entered. Both of these are kind of confirming things that the calculator puts that are for you, that are available to you. Alright, p-value is it. P-value is what we're after here, right? So step 2 is done. We've computed the p-value using the TI calculator. Now step 3. This is where we determine whether or not the data is significant. We'll compare our p-value to our significance level. Now remember, small p-values suggest H0 is false. Large p-values suggest H0 is true. I usually make a little table like this. P-value and significance level. Our p-value, as we know, our calculator computed it to be 0.262. The alpha level, which is typically given to you in the statement of the problem, you recall the significance level, or level of significance, was, we were told to use 0.05. and I'll claim that the p-value is greater than alpha, and in that case I will fail to reject H0. Let me show you why. I'll say large p-values suggest H0 is true. In other words, our data isn't strong enough to warrant rejecting the null claim or the null hypothesis. Well, large p-values, you may say, how large? Well, larger than alpha. All right, so large p-values suggest H0 is true. So in that case, if my p-value is greater than alpha, I fail to reject the null hypothesis. Remember, your answer to these hypothesis test questions is either going to be reject H0 or fail to reject H0. All right, I claim in this case that the sample data is not statistically significant. With regard to rejecting H0. It's not extreme enough. And if we look back, that sample proportion of 0.11, what was it? I'm looking here. The sample proportion of 0.118 wasn't far enough away from 0.1 to warrant rejection of that null claim. Alright, so this you might call an interpretive statement. Sample data is not statistically significant with regard to rejecting H0. In other words, my sample proportion of 0.118 is not extreme enough. To reject the null claim. Okay? Remember, H0, H1, there's always this analogy in most statistics textbooks. H0 is kind of like the assumption of innocence in a court of law. And you don't want to claim someone guilty unless you're very, very sure they are not innocent. Okay? So I like to call H0 as the king of the hill, and H1 is like the challenger, the challenging claim. All right, the challenger maybe has to work a little harder to unseat the king of the hill, right? All right, so summary. In hypothesis tests, now the book goes through, I think they've got it, I think as many as 8 steps in these hypothesis tests. I break it down to 3 steps. In any hypothesis test, step 1 would always be to clearly state the hypotheses, and that you have to dig out from the verbiage in the problem statement. Step 2, in any hypothesis test, compute the p-value. We will be using the p-value approach in all hypothesis tests in this course, and of course the calculator will grind that out for us under the test submenu. And step 3 would be to compare the p-value to alpha and make a conclusion about H0, either reject or fail to reject. Alright, let me get a fresh screen and we'll run through another couple of examples. We just did a right-tail test, so let me see if we can grind out a, let's see, hang on. Yes, let's do a two-tailed test now. And I'm looking at number 18. I believe this is in our homework list on page 409. You might want to turn there and read along. Perception and reality. In a presidential election, 308 out of 611 voters surveyed said that they voted for the candidate who won. Use a 0.1 significance level to test the claim that among all voters, the percentage who believe that they voted for the winning candidate is equal to 43%, or 0.43, which is the actual percentage of votes for the winning candidate. Alright, so from our sample data, well, we've got 611 voters. Out of those 611 voters surveyed, 308 said that they voted for the winning candidate. Use a 0.1 significance level to test the claim that among all voters, the percentage who believe they voted for the winner is equal to 0.43. Well, percentage is like a proportion. I'm going to say the proportion equals 0.43, or 43%. This will translate to a null claim. Right? The alternative claim is then what? Well, if the null claim is given as p equals 0.43, then by implication, H1 is going to be the alternative claim, p is not equal to 0.43. So, again, the statement of the hypotheses you have to sometimes unravel from the context of the problem. So I'll call this step 1. H1 is given as an equality. Remember, H0 is always an equality. And H1, if they don't say greater than or less than, well, then you have to assume not equal to. Okay, so this is going to be a two-tailed test. Two-tailed hypothesis test because the symbol in H1 by implication is a not equal to statement. Alright, I think we have everything we need to continue on and compute the p-value of the sample data. Alright, again, go to one-prop z-test command under the test submenu, p sub 0. The TI lingo for the null claim is that p equals 43%, or I'll say 0.43. So enter that in under the P0 entry. Raw count of people who surveyed said they voted for the winner. That was 308. And little n is, of course, 611. Alright, I punch this out on my calculator, and from this sample data, I get a p-value. Remember, it's the third line on your output screen, a results screen. Your p-value is 2.16 e minus 4. Now remember, this is scientific notation. In decimal, it would be equal to 0.000216, a very small number, right? Alright, once we get the p-value, step 3 is to compare and conclude your results. Again, I'll make a little mini table here with my p-value right next to my alpha level, my significance level, to tell me if my data is significant with regard to rejecting the null claim. So my p-value is 0.000216. The alpha level was given as 0.10, and typically that's given to you in the problem statement. And certainly my p-value is much less than alpha. And remember the little slogan here, small p-values suggest H0 is false. Small p-values mean extreme data values. Right? How small? Smaller than alpha. Right? If your p-value is smaller than alpha, right, we suggest H0 is false. Hence my conclusion, for this hypothesis test would be to reject H0. That's my conclusion. As an interpretive statement, well, I'm reading out of the book here, out of the author's manual. There is sufficient evidence to warrant rejection of the claim that the percentage who believe that they voted for the winner is equal to 0.43. Write that down. Interpret. Sufficient evidence, or statistically significant evidence, exists in the form of sample data to warrant rejection of the claim that proportion or percentage of voters for the winner, or the winning candidate, equals 0.43 or 43%. Okay? Alright, so we've done a right-tailed test, we've done a two-tailed test, and I want to run through a left-tailed test before we call it a day. This is number 26 in our homework list on page 410. And let me read through this. Kind of a scenario we've seen in earlier chapters in our book. Talks about job interviews and having body piercings and tattoos in a job interview. In a Harris poll of 514 human resource professionals, write that down. So we're surveying 514 human resource professionals. 45.9% said that body piercings were big grooming red flags. Okay? Use a 0.01 significance level to test the claim that less than half of all human resource professionals say that body piercings are big grooming red flags. Alright, so my significance level is going to be 0.01. Now, according to the sample, it said 45.9% said that body piercings were red flags. Well, that reveals a sample proportion of 0.459 or 45.9%. Notice, a raw count of those who believe body piercings are red flags is not given. Raw count not given. Alright, so we've got to take a little bit of a mini step to figure that out independently. X equals, well, what's the raw count going to be? If you've got this proportion in your sample and you've got this many in your sample, X is going to be, well, it's going to be 45.9% or 0.459 times your sample size of 514. Notice, let me write that out again. Because p hat is your raw count over n, right? Well, we know p hat is 0.459, our sample proportion. X, we don't know the raw count, and n is 514. All right, we can certainly solve this equation for x pretty easily. X will be, if I punch it out, the calculator says 235 and change. Now you must round up to enter this raw count into your calculator. So that's a finer point of the game here. My raw count here, I'm going to have to round that up to 236 to satisfy my calculator restrictions. Alright, so I've got everything I need. I've got a sample size, I've got a raw count, I've got a significance level. Here we go. Step 1. State the hypotheses. Well, again, looking at the problem, it says test the claim that less than half say body piercings are red flags. Less than half. Well, that means the population proportion of human resource professionals who believe that grooming or that piercings are a red flag is less than half, or less than 0.5. Remember, H1 is always an inequality statement, so I will label that claim as H1. What would H0 be then? Well, H0, of course, is the corresponding equality, that the population proportion of human resource professionals who believe piercings are red flags equals 0.5. Alright, so step 1 is done. I've stated the hypotheses. Step 2. Compute the p-value. Well, again, I'll go to my one prop z-test command. I'll enter in p sub 0. Well, again, that's the TI lingo for the null claim, and that's going to be 0.5. My x value, as stated before, we're going to have to use 236 as our best approximation for the raw count of those human resource professionals that say piercings are a red flag. 236. I'm going to select a left-tailed test. Our prop command would then be for a left-tailed test. I've got 3 choices. This is a left-tailed test as determined by the sign in our H1 statement. And I then calculate and enter, and my result for p-value would then be 0.032. So p-value pretty much tells it all in these hypothesis tests. Step 3, little mini table, p-value and alpha. Well, is our p-value significant? Well, we've got to check it against the given significance level. And what was it here? Let me check. 0.01. Alright, your p-value is clearly greater than alpha, about 3 times greater than alpha. So, remember the slogan, large p-values suggest H0 is true. There's nothing wrong with H0, possibly. Right, so my conclusion here would be to fail to reject H0. And again, your conclusion should be either to reject or fail to reject H0. We can interpret this with a statement. I'm looking at the textbook. The author is claiming here there is not sufficient evidence to support the claim that less than half of all human resource people say body piercings are red flags. Right? So there is not sufficient evidence. In other words, your sample proportion wasn't extreme enough to warrant rejecting the claim that half of all HR human resource people feel piercings are big no-nos. The book says big red flags, okay? Alright, so we've given you a nice framework and 3 examples of hypothesis test, a left-tail test, a right-tail test, and a two-tail test. And we'll call it a day for section 8.3, testing claims about population proportions.